So let's look at a very difficult topic like lambda calculus. This is like quite often taught in universities, especially for computer science students. So what is lambda calculus? It's a very simple way to describe how functions work. So basically, it's the main. It comes from my. If you see my previous video on programming paradigms, it is a basis of functional programming. So everything is functions. So if you are into programming, you might know that you have variables, functions, and objects, classes, everything. But in functional programming, everything is a function. So it does not have use numbers, variables, or any loops. Nothing will be there. Everything is represented as functions. So that's the main concept. So lambda calculus is the math behind this programming, behind this concept. And for programming language like Python, JavaScript, and Java are some of the things which is based on lambda calculus. If you have used in Python the lambda function, which is like an anonymous function, it comes from this. Basically, the idea is input and function and output. So everything will be a function. So there is nothing to represent loops or variables. So that is the concept. So if you see lambda calculus history, it was like in 1930s by Alonzo Church introduced the lambda calculus. This is well before when we had any electronic devices or programming languages. There was no programming language. So this was a time when, so at that time they were defining this like a sort of so what do you say, template or a basis for today's programming languages. And it was quite important because that formed the fundamentals. Like if you read about lambda calculus, there's something called the Turing machine. And in this concept, like the Turing connection, where Church was developing the lambda calculus and Alan Turing was developing the Turing machine in the UK. So this both merged together, which was the foundation or birth of functional programming. It was still a math concept, but languages like Lisp, which was created in 1958, it is directly from Church's work. And if you have ever used lambda function in Python, if you see that there'll be like an arrow function and a bracket, which is like as same as in JavaScript. This comes from the this work. So okay, so that's being the very brief introduction of what lambda calculus is. I'm just talking theory here without showing what it is, but because I just want to go on the concept first. Then let's look at what is a Turing machine. Turing machine is like a simple imaginary computer invented to explain computers think. Like it was like what do you say? Before we had hardware to represent this. This is just a conceptual machine. How we have the modern computer. So it's like a very long tape, like a paper, and a head which can read and write symbols. So I think there's something like a punch card sort of thing where you have little holes, and when you feed these holes to a machine, it reads these holes. Yeah, so this is like a program. Yeah, so that was the initial time when we had sort of a program. So even it's very basic, and Turing machine can do everything which a computer can do, but it's a bit of slow. So you can say this is the machine which was like what do you say, the first computers in concept. Yeah, so that's the basis. So let's look at the third point, like what does lambda calculus solve? So why at all lambda calculus? Yeah, so basically what the idea of lambda calculus solves is like it defines what is computability. Yeah, so along with Alan's Turing machine, lambda calculus was the foundation for these theses. And this thesis basically states that anything that can be computed by a human following a set of rules can be computed by lambda calculus. So that's the basic idea. So like for example, how when you write a program, how you make the decision. So this was in 1928, David Hilbert asked the Entscheidungsproblem, the decision problem. That is there an algorithm that can take logical statement and tell if it's true or false? For now, when we are in program, we can easily note that you can put a if statement or a true or decision tree. All these things is easy to program, but in a time when there was no computers, where only mechanical devices and electrical devices were there, so this concept was like what do you say, the key point of today's programming languages or the thing. So this is the thing. So it basically it solves the function problem. That is the idea is to have everything as a function. So like in lambda function in Python, so it basically uses every variable, every loop as a function. So that's what it solves. Basically the computability is answering one, but can this problem be solved by a computer or a machine or not? So some problems are computable, meaning computer can always find a answer. In the sense computer, like meaning machine. Some problems are for example, what is a machine? Machine does a set of actions repetitively, right? That was in industrial revolution, there were a lot of machines which does the same thing again and again. So these are single purpose machines, but a computer was like a multi-purpose. It does actions based on what you instruct it to do. So it's like a multi-purpose machine. So that's the thing which it basically solves. It solves the computability issue. So this, imagine, this was all, this thought came like before we had computers. Yeah, after you had computers, then you can speak about how things work, but these were done before. So this was the foundation. So like example is adding numbers, sorting lists, knowing if everything is program or a loop. So this is the main thing. So if you don't understand like most you just catch some of the ideas, it's fine, because it's a very complex topic. Yeah. And why are these topics important is because this is the foundation of computer science. That's why most of the universities teach, and how programming languages work, how computers can do some problems and other things. Yeah. So another thing which I want to mention is, compilers, right? Compilers, what does it do? It takes in like any English written code like Python or Java and converts it into machine code. And if you see compiler design, yeah, Lambda Calculus plays an important role in this, because like why compilers is related to Lambda Calculus is like because the intermediate representation. So when you write a complex code, the compiler basically needs to simplify it to perform optimization. So many compilers basically translate your code into simplified functional code or forms. Yeah. So initially the Haskell, GHC Haskell, and the comp cert compiler uses the core, which is the basically essentially tiny typed Lambda Calculus, or C compiler use the functional logic to prove that the compiler doesn't have bugs. So basically compiler, what does it do? It basically checks your code and matches or solves and matches the patterns. If your code is following the rules of, for example, a C coding style, then it just tells you if there's error or not. Yeah. So this is the fundamental. So in compiler design, Lambda Calculus does exactly all sort of same. So Lambda Calculus provides the mathematical rules for lexical scoping. Yeah. So that's the basic idea. So compilers use these rules to build sort of a syntax trees to manage certain things. Yeah. So this is the idea. So I'm not going into detail. Just keep in mind, like, it is Lambda Calculus is like sort of very important in terms of compiler design and compilers, how compilers work.